All right, let's dive in. Today, we're talking about the secret rules that connect pretty much everything, from your social circle to your computer's data. And we're going to do it using the awesome power of mathematical relations. So, here's a thought for you. What could a family tree and a computer network possibly have in common? I mean, one's about people and history, the other is all about digital code and wires. But here's the kicker. They're both built on the very same idea, a relationship. And we're about to see exactly how. So, to really get a grip on these connections, we've got to give them some structure. In this first part, we're going to break down what it means to make a relationship, mathematical. And honestly, that's all it is. Seriously, before you think about complicated formulas, just picture this. A mathematical relation is just a list. It's a way of writing down who's connected to what. For instance, is a parent of. That's a relation. Or is friends with on a social network. Yep, that's a relation too. And we write these connections down in a super specific way, as an ordered pair. Now that word ordered is everything. Think about it. The pair you, your parent, means something totally different than your parent, you. In math, just like in the real world, the direction of the connection is a huge deal.
Okay, so we've got these lists of connections, but here's where it gets really interesting. It turns out a whole bunch of these relations follow a few simple but unbelievably powerful hidden rules. So let's pull back the curtain and find out what they are.
Let's kick things off with what I like to call the mirror test. It's a really simple question. Is something always related to itself? I mean, take the equal sign. Is a number always equal to itself? Is A equals A always true? Of course it is. This mirror test has a formal name in math, the reflexive property. A relation is reflexive if every single thing in our group is related to itself. So if we're talking about the numbers 1, 2, and 3, a reflexive relation has to have the pairs 1, 1, 2, 2, and 3, 3. It's all or nothing. Next up, let's try the two-way street test. If there's a connection going one way, does it automatically have to go back the other way? For instance, if you have a sibling, you are their sibling, and they are your sibling. It's a two-way street. But what about is a parent of? If you're a parent to your child, is your child a parent to you? Definitely not. That's a one-way street for sure. And this is the symmetric property. It just means that for any connection, A, B, that we have on our list, the reverse connection, B, A, has got to be on that list too. It's a perfect two-way street. And last but not least, we have the chain reaction test. Think about this. If we know that 5 is greater than 3, and we also know that 3 is greater than 2, does that automatically mean 5 is greater than 2? Yeah, of course it does. It's this idea that a link from A to B, and then from B to C, can create a kind of shortcut, a direct link from A to C. This whole chain reaction thing is called the transitive property. You probably know it better as the friend of a friend rule. If you're friends with Bob, and Bob's friends with Carol, you can make a connection to Carol. So if A, B is in our set, and B, C is in our set, then for it to be transitive, the shortcut pair, A, C, must also be there. So there we have it, our three big rules, reflexive, symmetric, and transitive. Now, theory time is over. Let's get our hands dirty, play detective, and see how these rules work with some real examples. Okay, here's our first suspect. This relation is defined on the set of numbers 1, 2, 3, and 4. Let's run it through our 3 tests and see what we find out. So, let's see the results. Is it reflexive? We check for the mirror pairs. Do we have 1, 1, 2, 2, 3, 3, and 4, 4? Yep, all there. So that's a yes. Symmetric. Well, let's see. We have the pair 1, 2. Do we have its reverse, 2, 1? Yes, we do. So it's symmetric. And transitive. This one's a little tricky. We have the chain 1, 2, and 2, 1, so we need the shortcut 1, 1. And look at that. It's right there in our list. So it passes all 3 tests.
All right, let's try a different one. This relation looks a lot simpler, right? It's just a straight-up chain. Let's see how it holds up against our 3 rules. And the verdict is a total strikeout. It fails on every single count. Why? Well, it's not reflexive because we're missing 1, 1, 2, 2, all of them. It's not symmetric because we have 1, 2, but where's its reverse? 2, 1. Nowhere to be found. And you won't believe it, it's not even transitive. The chain is broken. We see a link from 1 to 2 and a link from 2 to 3, but the required shortcut from 1 to 3 just isn't there. Okay, now that we know the rules these relations play by, let's take a quick look at their basic anatomy, the fundamental parts that make them what they are. Every single relation has two key components. First, there's the domain. That's just a fancy word for all the unique starting points, all the first numbers in our pairs. Then you have the range, and you guessed it, that's the set of all the unique ending points, all the second numbers, starting points and ending points. That's it. Let's look at this example right here. To find the domain, we just go through and grab all the unique first numbers. So we have a 1, another 1, so we just count it once. Then a 2 and a 3. Boom! The domain is 1, 2, 3. Now for the range, we do the same for the second numbers. We have a 1, a 2, a 3, and another 1. So the range is also 1, 2, 3. So what happens if you have two different relations, like R and S here? Well, you can combine them. It's called taking the union. And really, it's just creating one big new relation that includes every single connection from both of the original lists. Just think of it like merging two different address books into one. And here's the result. It's one big set that has every pair from R and every pair from S. But notice, pairs that were in both lists, like 1, 2 and 3, 3, they only get listed once. The union is all about the unique connections from both sets combined. No duplicates allowed. Okay, so we've talked about ordered pairs, these three hidden rules, a relation's anatomy, and you might be sitting there thinking, this is cool and all, but why does this abstract math stuff actually matter? Well, let's zoom out, because this is where it all connects back to our world.
This is not just some dusty theory in a textbook. This is the secret engine that runs our digital lives. When a database finds everyone with an age greater than 30, that's a relation. When a social network suggests friends of friends, that's transitivity right there in action. Even something like booking a flight with a layover relies on a transitive relation to get you from your home city to your final destination. These simple rules are the bedrock logic that makes all our complex systems actually work. So, we've seen that just beneath the surface of everything from family trees to computer networks lie these simple, elegant rules. Our world is literally built on a web of connections that can be reflexive, symmetric, or transitive. So the real question is, now that you've seen the blueprint, what other hidden relationships are you going to start seeing all around you?